Imagine you've just been selected for the most ambitious mission in human history. Not Mars, not the asteroid belt. Neptune, the 8th planet, the ice giant so far away that the light reaching your eyes right now left it over 4 hours ago. You accept, you train, you launch. And here's the part no one tells you before you go. You will never come home. Not because of a catastrophic accident, not because the mission fails, but because the journey itself, the sheer physics of it, will make returning to Earth virtually impossible. This isn't pessimism, it's math. And math, unlike ambition, doesn't negotiate. So let's talk about what a Neptune mission would actually look like, and why, step by step, the universe makes it a one-way ticket. Before we go any further, we need to calibrate your intuition, because most people hear Neptune is far away and nod politely, without truly grasping what that means. So let's start close. The Moon is about 384,000 kilometers from Earth. Light crosses that distance in just over a second. Apollo astronauts made the trip in 3 days. We think of the Moon as distant, and on a human scale, it is. Now zoom out. Mars, at its closest, is about 55 million kilometers away. That's 143 moon distances stacked in a line. A spacecraft takes 6 to 9 months to get there. Now, forget both of those. Neptune is, on average, about 4.4 billion kilometers from Earth. Not million, billion. That's roughly 80 times farther than Mars at its closest. Light itself, the fastest thing in the universe, takes over 4 hours to travel that distance. If something went catastrophically wrong on your spacecraft near Neptune and you sent a distress signal, Earth wouldn't receive it for 4 hours. A response couldn't arrive for another 4. You're not delayed, you're isolated. To make this even more concrete, the only spacecraft to ever visit Neptune was Voyager 2. It launched in 1977. It arrived at Neptune in 1989, 12 years. As of 2025, Voyager 2 continues transmitting from interstellar space, over 130 astronomical units from Earth. And Voyager 2 wasn't hauling crew quarters, life support, food, water, return fuel, or any of the equipment a human mission would require. It was a lightweight probe powered by radioisotope thermoelectric generators on a one-way trip using a rare planetary alignment that won't repeat for another century. That's where the first wall appears, and it's not the last. Let's talk about getting there and why it's one of the most brutal problems in all of physics. To reach Neptune in any reasonable time frame, you don't just need thrust, you need sustained thrust. Chemical rockets, the kind that have powered every crewed mission in history, deliver short, intense bursts of energy. After launch, the spacecraft coasts. It glides through space on momentum alone, occasionally firing small correction burns. This is efficient within the inner solar system. For Neptune, it's catastrophically slow. A Hohmann transfer orbit, the fuel-efficient elliptical path used for most planetary missions, would take roughly 12 years to reach Neptune. 12 years of weightlessness, 12 years of cosmic radiation, 12 years of recycled air and water, 12 years in a metal container the size of a studio apartment. But here's the catch. If you want to arrive at Neptune and not just fly past it like Voyager 2 did, you also have to slow down. That requires burning more fuel, and the fuel to slow down has to be carried all the way from Earth, which means more mass, which means more fuel to accelerate, which means still more mass at launch. This is the rocket equation. Engineers call it tyrannical for a reason. Every kilogram of propellant you add to handle the return journey requires even more propellant to carry that propellant. the math spirals. A crewed Neptune mission, carrying enough fuel for a two-way trip with orbital insertion, would require a spacecraft so massive that no launch system on Earth today could put it into orbit. You'd essentially need to build a small space station first. On paper, faster propulsion systems exist as concepts. Nuclear thermal propulsion could theoretically reduce travel time to 5 or 6 years. Nuclear electric propulsion, Vasmer ion drives, fusion drives, laser-pushed light sails, all theoretically promising, none ready for a crewed mission. Even with nuclear propulsion, you're still talking about years of travel in each direction. And you're still subject to everything that years of space travel do to a human body. That's where the problem gets personal. But before we get to the biology, we need to talk about where you're actually going. Because Neptune isn't just far, it's hostile in ways that are difficult to overstate. Neptune is classified as an ice giant. That name is somewhat misleading. There's no surface to land on, no frozen plain waiting for boot prints. Beneath the upper atmosphere, a swirling mass of hydrogen, helium, and methane that gives the planet its deep cobalt blue, lies a churning ocean of water, ammonia, and methane in a superheated, superpressurized state that defies easy description. Not quite liquid, not quite gas, something else entirely. Wind speeds on Neptune reach over 2,000 kilometers per hour. That's roughly 6 times the speed of the most powerful hurricanes ever recorded on Earth. The Great Dark Spot, a storm system observed by Voyager 2, was comparable in size to Earth itself. And unlike Jupiter's storms, which appear to be long-lived features of the atmosphere, Neptune's storms seem to appear and vanish over timescales of years, which means we still don't fully understand the dynamics driving them. Recent observations from the James Webb Space Telescope have revealed new details about Neptune's atmospheric structure, confirming the planet's bizarre seasonal patterns despite its 165-year orbit. The planet also has a deeply strange magnetic field. On Earth, our magnetic field is roughly aligned with our rotational axis, which is why compasses point roughly north. Neptune's magnetic field is tilted about 47 degrees from its rotation axis and offset significantly from the planet's center. Models suggest this indicates the magnetic field is generated not in a central core, like Earth's, but somewhere in the icy mantle layer, a mechanism we don't fully understand. And then there's Triton. Neptune's largest moon is one of the most geologically active bodies in the solar system, and arguably one of the most bizarre. It orbits Neptune backwards, in the opposite direction of Neptune's rotation, which almost certainly means it was captured from the outer solar system long after Neptune formed. Its surface temperature hovers around -235 degrees Celsius, making it one of the coldest known objects in the solar system. And yet it has active geysers, nitrogen geysers, erupting through a thin crust of frozen nitrogen and methane, shooting plumes of dark material several kilometers into the near vacuum of its tenuous atmosphere. Neptune's second moon, Nereid, follows an extremely eccentric orbit that takes it from 1.4 to 9.6 million kilometers from Neptune, further evidence of the chaotic capture events that shaped this distant system. Triton is also slowly spiraling inward. In roughly 3.6 billion years, tidal forces will tear it apart, and Neptune will briefly have a ring system more spectacular than Saturn's. We won't be around to see it, but the fact that we know it is coming is a reminder of what physics does on long enough timescales. It doesn't preserve, it dismantles. This is the world you'd be going to, alien in nearly every dimension, and the planet itself is only one layer of the problem. We covered the basics in Mars mission discussions, but Neptune changes the scale so dramatically that every single biological problem becomes categorically worse. Start with radiation. Earth's magnetic field and atmosphere block roughly 99.9% of incoming cosmic radiation. In deep space, past Mars, past Jupiter, past Saturn, that protection doesn't exist. Astronauts on the ISS receive about 150 millisieverts of radiation per year, which is already 50 times more than the average person on Earth. In deep space, beyond Earth's magnetosphere, that number increases further. NASA's current career radiation limit for astronauts is 1 sievert, equivalent to 1,000 millisieverts. That's the threshold above which the lifetime risk of fatal cancer increases by roughly 3%. A one-way trip to Neptune, 5 to 12 years depending on propulsion, would likely deliver a radiation dose several times that limit before the astronaut even arrived. Every year adds more. Every year, the DNA damage accumulates. The cell repair mechanisms can't keep pace. The body quietly, relentlessly falls apart at the molecular level. There's no shielding that fully solves this. Thick metal shielding actually makes things worse by creating secondary radiation when high-energy particles strike the hull. Water can help, but water is heavy, and heavy is the enemy. Now add weightlessness. Without gravity, bones lose 1 to 3% of their density every month. On a 6-month ISS mission, that's manageable with 2 hours of daily exercise. But on a 12-year journey to Neptune, the math becomes grotesque. At even 1% per month, 12 years represents a theoretical loss of 144% of original bone mass, which is, of course, impossible. What actually happens is that the body reaches a catastrophic equilibrium well below normal density long before then. Hip bones, femurs, the spine, the exact structures that hold a human upright under gravity. They don't just weaken, they become brittle, porous. The skeleton of an elderly person with severe osteoporosis in the body of someone who might be in their 40s. The heart follows the same logic. On Earth, the heart pumps blood upward against gravity constantly. That constant work keeps it strong. In weightlessness, that resistance vanishes. The heart adapts. It atrophies. Studies show it can lose up to 20% of its mass during extended missions. Blood volume drops. The cardiovascular system reconfigures itself for a world without gravity. And the eyes. Fluid pressure rises in the skull in weightlessness. The optic nerve swells. The shape of the eye changes. Some astronauts return from 6-month missions with permanent vision damage. On a 12-year journey, you'd arrive at Neptune, if you arrived at all, with eyes that may no longer function the way they did when you left. You might think that's the hardest part. It isn't. Because all of that, the radiation, the bone loss, the cardiac atrophy, that's the outbound trip. That's before you've done anything, before a single scientific measurement at Neptune, before you've even tried to enter orbit. Now think about the return. Assume, charitably, that the crew spends 18 months at Neptune. Maybe they orbit. Maybe they descend toward Triton, studying those nitrogen geysers from close range, gathering data no robot has ever been equipped to collect. Then another 12 years back. That's 25 years in space, at minimum. The human body that arrives back at Earth is not the human body that left. Bone density is a fraction of what it was. Muscles have wasted in ways that years of rehabilitation might not fully reverse. The heart has forgotten how to work against gravity. Standing up, just standing up, could cause the cardiovascular system to fail. Some ISS astronauts who spent 6 months in orbit need weeks to walk again. A Neptune astronaut would need to relearn what gravity means to a body that spent a quarter century forgetting. And that's assuming the psychological structure held together. Here's the part that's hardest to quantify. A Neptune crew would be more isolated than any humans in history. The communication delay alone, 4 hours for a signal to reach Earth, 4 hours for a reply, means there's no real-time contact with anyone. Ever. Not for 25 years. No live conversation. No spontaneous human connection from outside the crew. Just a small group of people, confined, irradiated, physically deteriorating, circling a blue ice giant 4.4 billion kilometers from everyone they've ever known. Studies from isolation experiments like the Mars 500 simulation and high seas habitat research show measurable psychological deterioration after just months of confinement. We're talking about decades. Think about what that actually means for the texture of daily life. Every piece of news from Earth arrives already hours old. A death in the family, a disaster, a discovery. You find out, and by the time your grief or your joy reaches home, another 8 hours have passed. The emotional rhythm of being connected to other people, something so fundamental we rarely even name it, simply doesn't exist. The crew becomes, in every practical sense, its own civilization, its own unit of humanity, sealed off from the rest of our species by physics. Even carefully selected, extensively trained individuals break down psychologically under extended isolation. Studies on Antarctic winter rovers, submarine crews, and simulated Mars missions show measurable cognitive decline, conflict escalation, and emotional deterioration over months. Those studies lasted months. We're talking years. Years in which the same small group of people must trust each other completely, resolve every conflict internally with no outside arbitration, and sustain motivation for a mission whose destination becomes a daily reality rather than a distant goal. There's no escape hatch, no mediation team on standby, no option to walk away. Whatever happens in that spacecraft, whatever fractures or grief or exhaustion accumulates, stays in that spacecraft. The mission wouldn't just need astronauts, it would need people willing to accept that the person who returns, if anyone returns, is not quite the same person who left. And that Earth, after 25 years, would barely resemble the world they knew. So where does that leave us? Let's be precise about this. A crewed Neptune mission isn't impossible because of a single unsolvable problem. It's impossible because of a chain of problems, each one severe on its own, that compound each other into something that defeats current human capability entirely. The distance makes travel times measured in decades unavoidable without propulsion technology we don't yet have. The travel time means radiation exposure that exceeds safe limits several times over. The radiation and weightlessness mean the body that arrives is medically compromised before the real mission even begins. The fuel requirements for a return trip may make that return physically impossible to launch in the first place. And the communication blackout means the crew is, in every meaningful sense, alone. This isn't a mission that kills through a single dramatic failure. It's a mission that grinds you down across decades, through physics, through biology, through the quiet erosion of everything the human body and mind were built for. That said, and this is important, Neptune isn't beyond reach in a scientific sense. Voyager 2 has given us breathtaking images. The deep cobalt blue of the planet, the pale arcs of its faint rings, the frozen surface of Triton. Future robotic missions, equipped with advanced propulsion, could reach Neptune in years rather than decades. Proposed Neptune orbiter concepts like NASA's Trident mission could map the atmosphere, measure the magnetic field, sample the upper cloud layers. We can explore Neptune, we just can't send people there yet. Not safely. Not with any reasonable expectation that they'd come back whole. Neptune is a reminder that the universe doesn't scale to human timelines. It doesn't care about launch windows or career limits, or the fact that a 25-year mission is longer than some children grow up to be before a parent leaves. Physics sets the terms. We work within them, or we wait until we understand them better. The stars are patient. We're the ones who aren't. I hope you enjoyed the video. If you did, a like or subscription helps more people find it. See you next time.